Okay, so in this video, we're going to be talking a bit about parametric and symmetric equations of a line in 2D and 3D space. Okay, so before we begin, let me just draw some lines. Okay, suppose that this is my plane here, right? These are my, so this is my z-axis, this is my y, and this is my x. Okay, so suppose that we have a line in the xy plane here, right? So the equation of the line can be written here. So let me draw it again. Let me draw a line. Can be written in something called the point slope form. So let's make it a little bit slopey. There we go. Right? So we have this line here. Let's call this line something. Let's call it L. So L is this line here, right? So just like in 2D space, a line in 3D space is determined when we know a point, right, on this line L and the direction of L, which way is L going, right? So this point here, let's call it point P0, X0. So it's going to be somewhere here. So let's, okay. So let's say it's somewhere here, right? We're just taking an arbitrary point, and let's call this point here P0. It'll be X0, Y0, Z0, right? Right, so we have set up our diagram here now. So in 3D space, we said, right, the direction of a line, so we conveniently describe this to be a vector. Let's call the vector something. Let's say it's V. So let's draw a vector here. Let's use a different color. So suppose that this is, so we're going from the origin here. Let's say this is V here, right? So this is V. This is my vector V. And we're going to take another point. Let's take another point on this line here. Now this point here is P0, X0, Y0, Z0. We're going to take another point from here. So let's use a different color again. And this point is also going to be on L. Let's say it's somewhere here, right? And this point is going to be, so let's say this is P, this is X, Y, Z. So we were saying before that in 3D space, the direction of a line is conveniently described by a vector. And we let V here be a vector that is parallel to this line L. So L is going like this. So just imagine that V here is parallel to this line here. Okay? Although it's not really drawn to scale. So let this point here, P, X, Y, Z, be an arbitrary point on L. Now we're missing two pieces of information. So we're going to let something new, and we're going to call that something R0 and R. Are we going to be that, let that be position vectors of P0 and P, right? So we have to draw that as well. So R0, let's take R0 to be somewhere maybe here. And let's take R. Oh, we already have R. R is this line, this brown line here. Okay, so this is R here. So this one here is R0. This one here is R. This is V. This is my line L. So now, suppose that we have some vector, right? On this line here L. So suppose that we have on this line here, L, we have some vector on the line L. Let's call this vector something like A, right? So if A is a vector, right, and A is obviously represented by P0, so A is represented by P0P, that's the direction, then what do we remember from our previous knowledge of math, right? How do we find R here? R will just be R0, which is this here. So imagine this here is a triangle, R0 plus A, right? So that's what R is. So R0, R is just R0 plus A. But what did we say at the beginning? A and this vector V here are parallel to each other. So because that happens, let me write here. So let's write it in words. So since A and V are parallel vectors, then there exists a scalar K or T or lambda. Lambda is one of the more popular ones. Let's use T, just to be a little bit different. So there exists a scalar, let's say T, such that A is equal to T, which is my scalar, by V. So from this now, combining this new information with the fact that R is equal to R0 plus A, then we arrive at something that is called the vector equation of a line. So we have the vector equation of a line. And that is written as, let's write it in red, that is equal to R is equal to R0 plus my scalar, I use T, some people use lambda, and that's fine as well, by V, right? So this here is called my vector equation of a line. Let me put it in a nice box. So we see that our parameter here, right, T, each value of this parameter T, what does it serve? It gives the position vector R of a point on this line L. So it's easier for us to see that as this value of T, our scalar, right, as T varies, the line here that is traced out by this here, this tip of this vector R. So we have positive values of T that correspond to points that lie on the other side of P0. Right? Because remember, this is the entire line L here. So if the vector V, this vector V here, that gives the direction of the line L, because remember they are parallel, right? So this is going like the same direction like this. So if the vector V that gives the direction of the line L is written in another form, which is called component form. So if we write V, so let's write it. So if V if the vector V that gives the direction of L is written in something called component form, and form, right? Component form means that you write V is equal to A comma B comma C, right? So we are trying to ease our way into 3D space, right? Then what? Then our scalar T by V is just introducing t inside here. So this becomes ta, or lambda a, or whatever your scalar is, maybe k, by tb by tc. So therefore, this means that r, let's go back up to my polygon diagram, r here is this coordinate here, xyz, right? So what is r0? So r0 is just like p0 here, where you have x0, y0, z0. So if r is xyz, then r0 is x0, y0, z0, right? So then, so we could put and r0 is equal to x0, comma, y0, comma, z0, or and r, I forgot r, xyz. Right? So therefore, this equation here, right? Let's call it something. Let's call this equation number 1. So therefore, equation number 1 will become what? We can say therefore, equation 1 becomes r, which is x, y, z, is equal to, well, we already combined the scalar inside here, right? So we'll just have to write x0 plus t a, or lambda a, y0 plus tp, comma, z0 plus tc. Right? So we see here now that two vectors, so back to my diagram again, two vectors are equal if and only if the corresponding components are equal. Right? So let's write that down. That's kind of important. So two vectors are equal if and only if the corresponding components are equal. So from that, we have three important scalar equations here. This is the first one, second one, third one. So let's just extract that. So that tells me that x here is equal to x0 plus lambda, or at, y is equal to y0 plus bt, and z is equal to z0 plus ct, where t or lambda is real, right? Forgot that. Very important. Right? So these three equations now, should have written this in red. These three equations, put them in a box. These are called the parametric equations, right? So these are called the parametric equations of this line L, right? Of this line L, through this point P0, which is x0, y0, z0, and is parallel to this vector V. So we see that each value of my parameter here, which I introduced t or lambda or whatever, each value of the parameter will give a point, and this point is xyz on this line L, right? So these are my parametric equations here. So let's actually write that down. These are the parametric equations of the line L, big L, through the point P0, which is x0, y0, z0, and is parallel to the vector v is equal to a, b, c. Right, and each value we set of the parameter gives a point x, y, z on the line L. So these are the parametric equations. So far we have the vector equation of a line, and we have the parametric equations of a line, and you will need to interchangeably know these, right? Because sometimes you're given the parametric equations and then we have to convert it into another form. Okay, so now we're going to move on, or before we move on, let's actually do an example. Let's do an example. Suppose I have to find a vector equation and a parametric equation, because we just did that, that passes, not passes, so say, let's say we have to find the vector equation and the parametric equation for the line L, that passes through the point PT for point 5, 1, 3, and is parallel to the vector, let's call the vector I plus 4j minus 2k. Okay, so solution here. First thing first, what is R0? Right, we need to find, let's go all the way back up. We need to find R0. Right, of course we need v as well, but we are given v, right? V is equal to I whatever, some j, some k. So we need R0, but we are given R0 already here in our equation. R0 is, it says it passes through the point 513. So R0 is, so hence, so here, R0 is 5, 1, 3. So we have changed from the point with the curved braces here to this triangle one for the vector, right? Which is the same thing as 5i plus j plus 3k. So what is v again? V is given as I plus 4j minus 2k. So therefore, my equation using my scalar t will become, so r now is equal to 5i plus j plus 3k plus t into I plus 4j minus 2k. Right? So r is equal to 5 plus, well, t by I will just give me t, and then we could factor out the I and do the same for the rest. 1 plus 4t j plus 3 minus 2t by k. So using this now, what is my parametric form here? It's x0 plus 8t, etc., right? So it will be, we already factorized out the I here, so it will be this plus this, which means that my parametric equations are x is equal to 5 plus t, y is equal to 1 plus 4t, and z is equal to 3 minus 2t. Okay, so that is what my vector equation is over here, and my parametric equation here. Right, so this is how we would do this. Suppose, of course, further to this question here, suppose I was asked to find So this is a point on the line here. Are there other points on the line? Can I find another point on the line? Well, good thing for us that we have this parameter t here, so t varies. Remember what we said at the beginning here? This t can vary across this line here. So because that is true, so let's add another part. Determine 2 other points on the line. 2 other points on the line. So choose a value for the parameter. Let's choose t is equal to 1. When t is equal to 1, what is x? X is 6. Okay, so let's do that for the rest of them. When t is equal to 1, comma, x is equal to 6. And then what is y? Y will be equal to 5, and then z will be equal to 1. So another point on the line is 6, 5, 1. So put t now to be equal. So let's get another point. So let t be equal to -1. And do the same thing again over here. So when t is equal to -1, we get 4, -3, and 5. So another point could be 4, -3, 5. So we see that the vector equation and the parametric equation of a line are not unique. So let's write that down. So hence the vector and parametric equation of a line are not unique. So if you change the point of the parameter, right, then what happens? Or choose a different parallel vector, what happens here? The whole equation will change, right? So instead of what we had here, 5, 1, 3, we choose another point that says 6, 5, 1, right? Then the parametric equation of the line will be what? Instead of that, our new parametric equation would have been x is equal to 6 plus t, y is equal to 5 plus 4t, and z will be equal to 1 minus 2t. So that's what happens if you choose that. So, but if we stay with the 0.513, like we had before, right? But we chose a different, we chose another parallel vector. Let's just say we chose another parallel vector to be 2i plus 8j minus 4k. Then what happens to this parametric equation here? Right? It will change again. So we'll have x is equal to 5 plus 2t, y is equal to 1 plus 8t, and z is equal to 3 minus 4t. It changes again. So that tells me that, generally speaking, a vector, this vector v, which is what we had before, abc, that is used to describe the direction of a line L, right? And this illustrates this point here. Then as these things change, then the numbers a, b, and c, this a, b, and c from our vector equation from the beginning. Let's go back. B, a, b, c over here. These are called what? The direction numbers of L. A, B, and C are called the direction numbers of L. Okay? And since any parallel vector, or any vector, sorry, that is parallel to V here, could also be used, right, as well. Then we see that the numbers A, B, and C, which are called the direction numbers, right, are proportional to A, B, and C, right, and can also be used here as a set of direction numbers for L. So all of that is to say what? So all of that is to say that another way of describing here this line L at the beginning is to do away or get rid of this parameter t here altogether. Right? So we actually didn't label this equation. Let's call it equation 2. Right? We can do away with this parameter, and If none of these A, B's, and C's is 0, then we can solve each of these equations, right? So if you set them to equal to 0, right, then we could do away with the parameter and we can solve these three equations here for t, because t is consistent here throughout all these equations, and t is the parameter that stays the same. So if we do that, right, that long process, which isn't so long, then t becomes what? So t becomes x minus x0 upon a. T is also y minus y0 upon b. And t is also z minus z0 upon c. But t is the same throughout, which tells me that, okay, let me write this in red, which tells me that x minus x0 upon a is equal to y minus y0 upon b, which is the same thing as z minus z0 upon c. And all of this, right, all of this now, so we had parametric equation, these are called the symmetric, sy, equations of L, of, oops, symmetric equations of L. We're going to call this equation number 3. So we have the equation of vector equation of the line. We had parametric equations. Now we have symmetric equations of the line L. And notice something here. A, B, and C that appear over here as the denominators. So it has gone here from inside the equation. Let's go back. Right? Now these A, B's, and C's are now denominators here. Right? That appear over here. These here are the direction numbers of L. Right? That is that these are the components now of a vector that is parallel to L. So if perhaps A, B, or C, right, is equal to 0, then we can still eliminate T altogether. So if A was equal to 0, then we could eliminate. Okay, so let's write that. So if A is equal to 0, then we could write the equation, let's just say equations, because it's more than one, of L as x is equal to x0, x is equal to x0, and then of course y minus y0 remain the same. Okay? Right, so this means here that L lies on the vertical plane, right? X is equal to x0. So L lies in the vertical plane. X is equal to x0. So just like before, let's do an example here with this new, not new, but symmetric equations. Let's do an example. So suppose that we have, so this is example number 2. Let's use as well the parametric equations from before, right? So let's combine all the theory. So let's say find the parametric and symmetric equations of the line L that passes through the points, in more than one here. First point A, let's call A 2, 4, and let's call B another point. Let's keep it simple. Right? So here's the thing. Before we had V, but what is V here? We don't know, right? We aren't given the vector that is parallel to the line, but we can find it. So we can say Okay, so I should have written solution. So you could say here, we are not given a vector parallel to the line. Alright, but we can find it because the vector v, if we take the points a, b here, then we could find a, b. So we can find a, b, this vector here. How do we do that? Right? This is why we did the preliminaries of this, to understand how to add and subtract these vectors. So it'll be 3. What was b again? A is 3 minus 2, negative 1 minus 4, and 1 minus negative 3. So we have to find, so this is us finding AB here. So it's 3 minus 2, 4, 1 minus negative 3 vector. So we have 1 comma negative 5 comma 4. Okay, great. So what are the direction numbers here, right? Just to remind ourselves, it's 1, negative 5, 4. So let's take a point here now. So choose a point, A or B. I'm going to choose A, right? Let's start with A to make it easy for us. So let's take A as our point P0, right? So, and let's write. So taking A as P0, then the parametric equation, what it's gonna be? It's gonna be x is equal to 2. There's 2, right? Let's go back. 2 for negative 3. Okay, great. It'll be 2 plus t, because this is 1 here. Okay, great. Then it'll be y is equal to 4 minus 5t, and z is equal to negative 3 plus 4t. So these are my parametric equations. Now I need to find these symmetric equations. So lucky for us, we can interchange between these types of equations. So what is my first one here? So it'll be x minus this upon t was 1. Sorry, a. Then we have this is equal to y minus 4 upon negative 5. Negative 5. And the last one is z plus, because remember it's minus minus, so it'll be plus 3 upon 4. So these now are my symmetric equations. So this is symmetric equations. These are parametric equations here. Right? So this is how we would find this. So further to this, right? Suppose that we were asked, let's go back up to our diagram. Suppose that we were asked here, at what point does this line here intersect this xy plane? How would we find something like that? Well, didn't we just speak about setting certain values to 0 and then finding and eliminating parameters? So if you were asked at what point does this line intersect the xy plane? How would we find that? So the line here would intersect the xy plane when what happens? When what? Z is equal to 0. Right? So that is what will happen. So let's scroll down. Okay. So if it was another plane, maybe xz or something like that, then we would set something else to be equal to 0. So if we put z is equal to 0 here, then what happens? This here turns into 3 upon 4 because z is equal to 0. So that means I can write, so let's see. So we can say the line intersects the xy plane when z is equal to 0. So put z is equal to 0. So we just remain with x minus. So this will remain the same. This will remain the same. And this will become 3 upon 4. Right? So if we wanted to solve this now, we can solve this, right? So this, we can solve for x. We can solve for y here. Of course, z is equal to 0. My point, so z is already equal to 0. What is x here? Solve this. Let's divide and multiply. So we'll get x to be equal to 11 on 4. Put 11 on 4 back inside here and solve for y. And we get 1/4. So this is the point here that the line intersects the xy plane, right? So this is how we would do a question like this, right? So this video was to cover symmetric and parametric and the vector equation of the line. As we move forward with this course, the next part that we will look at is skew lines, right? And then from skew lines, after that, we will start to look more at planes itself. Okay, so that's the end of this one.